Hey, how y'all doing? Right on. So, as you said, my name's Cody. I work for a company called Kixer. We do machine learning for advertising. We were successfully acquired a little over a year ago, so if this kind of stuff sounds cool to you, we're always looking for good engineers. Come talk to me. So, horizontally scalable relational databases, like that's a mouthful. What is it that I'm talking about? So, we had a single Amazon RDS database instance that we were using, not for serving live ad traffic, but for doing customer-facing analytics and financial reporting. And we were running into capacity limits on what you can put on one RDS database. So what do you do when you have a problem that's too big for one machine? You split it up into different pieces or shards. You put each shard on a different machine. If I had told you that this talk was about sharded databases, you probably would have said, what is this, 1999? I don't want my application to have to worry about which database it's talking to for which particular piece of information. I don't want to deal with that either. I would rather use a tool to do it. In this case, the tool we're using is called Citus. You can basically think of Citus as, what would I do if I was going to scale out Postgres? Oh, look, somebody's already done all that work for me. So you start with standard, normal, up-to-date Postgres. You install an extension just like any other Postgres extension. And what that does is extends the query planner so that it knows how to distribute your queries across multiple nodes. The reason I keep saying extension is that it's not a fork, so you're not stuck on like some 8 series ancient Postgres, right? Modern, up-to-date Postgres. Typically speaking, MPP databases like that are like mortgage the future of your company expensive. Citus is open source. There is a commercial company backing it. I don't work for them. I don't get paid to tell you that Citus is cool. We, in fact, pay them, and I will still tell you that Citus is cool. Special shout out to their product guy, Craig. He is legit, and he really knows his stuff. It's the extent of the promotion that I will do. My hope is that the underlying model that I'm talking about is straightforward and fundamental enough that this will apply regardless if you're using another database or rolling your own. So this is a Spark Summit. What does this have to do with Spark? So you can collect all the data you want, and you can do all the awesome Spark calculations you want. And unless you use that to answer questions that provide business value, you're not going to get paid. And if those questions are coming to you in live customer-facing traffic, you're going to have to serve those answers somehow. So if you're building a machine learning model with Spark, you can save that off in a format that you can load up into JVM, serve your traffic that way. If you're answering the kind of questions that you can pre-calculate all the answers to, you can use a key value store. And we do both of those things for use cases where it makes sense. There are some use cases, like what's been going on in the past 5 minutes, that I don't want to pre-calculate all the possible questions that a customer could ask about that, right? I can do some pre-aggregation, I can do some pre-filtering, but ultimately, when somebody's clicking on a dashboard, the question of what they want to see at that time is determined at runtime with runtime queries. So we're already using Spark SQL. It's pretty cool. Why don't we just use that to serve live traffic directly? So it turns out there's some pain points associated with that. Spark as a generalization is better suited for internally facing users where you're making queries that you care more about throughput than you do about latency. And in a customer-facing situation, you got lots of people that you don't control, that you would like to be able to share resources effectively and securely. And if they're each doing a dashboard where a given page load may have multiple queries backing it, you would prefer those queries to have execution times that are measured in millis, not hundreds of millis or seconds, right? Spark will continue to improve in that area. The next two things on this list are a little more inherent in the design of Spark and HDFS. So if I'm doing analytics and I'm in the advertising industry, it's probably no big surprise that I'm concerned with, say, counting impressions for a given number of times an ad has been shown. It's occasionally useful to be able to make mutable updates to a counter rather than counting some immutable record of every impression that's ever occurred for the context I care about. HDFS isn't really geared towards doing mutable writes. It's geared towards doing large immutable files. Similarly, if I care about how, say, clicks are related to impressions, it would be beneficial if those clicks and impressions for a given ad were written to the same machine to begin with, so that when I go to join them, I can do that join effectively without having to transfer any data. HDFS isn't really interested in letting you decide which node you're writing data to, and Spark will give you some degree of preference about the location that computation takes place, but it's a preference. It's not an absolute way of pinning data to a node. For people in the audience that are like, I serve live traffic with Spark SQL, and it's not that big a deal because I worked around it with blah, blah, blah. I'm not saying you're doing it wrong. I'm just saying I've been there, I've done that, there was pain involved. I spent some of the time wishing I had sharded Postgres instead. Now I do. Why did I wish that? If you look at these things from the point of view of a traditional relational database, they're pretty much bread and butter use cases, right? Got connection pooling options, got lots of secondary indexing options. If I want row-based storage, I can have it. If I want column-based storage, I can have it. And if I'm only on one node, clearly things are already co-located. Which brings us to, why don't people just use relational databases for everything? Common wisdom would have you believe that relational databases can't handle schemaless data, and that by the time you scale them out, you gave up everything that you liked about them to begin with. There's nothing inherent in the design of relational databases that makes this true. There are some things inherent in a distributed system that mean you may have to make trade-offs, but it's a continuum, not an absolute. And we were able to, and I believe you can, pick a point along that continuum that meets your needs. So let's look at each one of these in turn. Why am I putting schemaless in air quotes? If your data was schemaless, you wouldn't call it data. You would call it noise, right? You may need some flexibility for a given record, which fields and which types of things are present in it. Lowest common denominator for that sort of stuff is JSON. Turns out recent versions of Postgres are better at dealing with JSON than pretty much anything short of a dedicated document database. So you can create JSON columns as a first-class data structure, not just text. You can index over them efficiently. When you're querying them, you can use operators to drill down into the JSON. So what about scaling out? So your application connects to a master. It's just normal Postgres node, issues a normal Postgres query over JDBC or what have you. Query Planner is going to go look in some metadata tables, figure out which workers need to be queried to answer that, collect those results, ship them back to your application that's none the wiser. There are two things to pay attention to here. The first thing is this is not traditional scale out of read-only loads via read replicas. If you look at worker 1 here, it has 2 out of 4 shards. That means it's taking 2/4 of the read load. It's also only taking 2/4 of the write load. There is a table definition for your table on the master. It's empty. It doesn't take write load to disk. Second thing to pay attention to here is these boxes are just Postgres, right? I like simple solutions. You can tell that because I've got an ASCII flowchart on a slide. This is a simple known solution. If you're curious what's going on under the hood, go log into one of the workers, look at the tables, look at what queries are being run. Similarly on the master, the metadata is just in tables. So how do I actually get this data distributed? Well, it's going to get hashed. It's going to get put in a shard according to that hash. So I need to pick a key for that hash. And the choice there is determined at the time you define the table. And your trade-off is between, do you want queries hitting one shard, or do you want queries hitting all the shards? If you shard on something that's going to be commonly queried, like a customer ID, a given customer is only going to query using their customer ID. They're only going to hit one shard. That's good if you're trying to support lots of concurrent users. It makes joins very easy. The only downside is if you've got one customer that's like a 30-year load, you better be able to serve that off of one node. Other end of the spectrum, if you shard on something that's very evenly distributed, like an event GUID, nobody's going to query for, tell me all about event 0x deadbeef, right? They're going to do some kind of aggregation across everything. That's good if you're looking to exploit parallelism, and it makes sure that you don't have any hotspots. It's maybe bad if you need joins, right? So again, that's a trade-off, not an absolute. And if you need one query pattern that uses one way and another query pattern that uses the other way, just shard on both and keep 2 copies of the data. So how do I actually create one of these distributed tables? I define a completely normal Postgres table. In this case, super reductionist example. I've got an advertising ID for a given ad. I've got a website ID, some date, and a count of the events that have happened for that context. So I set a couple of Citus variables for how many copies I want, how many shards I want, call a function defined by the extension. I've got my distributed table. What does this actually do under the covers? If I go look on the master, I can see that it's made some inserts into these metadata tables, and I can see I've got 4 shards, they've got logical IDs, and a logical range of hash values that a given key is going to fall into that shard. Likewise, if I go look at the worker, I can see normal Postgres tables have been created, and they've got the shard ID appended to them. How do I write to this? I connect just like I would, and I do inserts, updates, bulk copies, whatever, and the master takes care of sending those writes to the correct node. If you need more write throughput, you can add more masters, or you can connect directly to workers as long as you hash correctly. We'll talk a little bit more about that later. OK, so hopefully it's clear how queries that hit one shard work. They're totally normal queries. What about aggregations? As long as the query planner is aware of your aggregate function and it knows it's associative and commutative, then it'll just work. So the example here is average. Clearly, you cannot go to one machine, get an average, go to another machine, get an average, pull those averages back to the master and average them and expect to get a good result, right? What do you need to do? You need to go to each worker. You need to get a sum and a count off of that each worker, pull the results back, sum up the sums and counts, then do your division. And that's exactly what the query planner is going to do. Hopefully, this is not surprising to anybody who's done any kind of aggregations in a distributed system. So if you're doing something that doesn't fit into that paradigm, you can usually do pre-filtering and pre-aggregation back to the master, at which point you write completely arbitrary SQL. What about joins? So I had mentioned impressions before. Now I've got clicks, and I want to compare clicks and impressions, right? If I if I distribute them on the same key, in this case, the advertising ID, they will end up on the same machine. And I can do a completely normal Postgres, non-distributed, no copying data join, and it will be fast. If I have a table that is not distributed on that same key, let's say by way of example, I have some sort of table of discounts for the price of a given click for a given date. This thing doesn't even have an ad ID in it. I can't join it on the same key. If I try to join it, Citus is going to warn me like, hey, you can do this, but it's not going to be able to use the real-time execution because it's going to be slow because I'm going to have to copy stuff. So if I say, no, really, I want to do this, I can still do it. It's just going to be slow. One way around that, as long as the table that you're joining is reasonably sized, by which I mean it fits on one node with room for the rest of your data. So we do this for tables with millions of rows, no problem, is I can just keep a copy on every worker, right? This is similar to Redshift dist all if you're familiar with Redshift. In this case, Citus is going to call this create reference table, and it will keep a complete copy of that table on each worker. So again, I can do the join with no shuffling of data around, and it's going to be a couple of orders of magnitude faster. All right, so what about transactions? It is debatable whether distributed transactions are even a good idea to begin with. Citus doesn't weigh in on that. It avoids the issue. There are other Postgres derivatives that try and play in that playground if you need to do some kind of crazy transaction of money between different machines. Individual worker transactions are still super useful, right? They're especially useful for Spark because Spark output actions are not exactly once outputs, right? They will get repeated in the case of a failure. Downstream transactions allow you to recover the equivalent of exactly once delivery semantics for actions that may be repeated. And again, to kind of echo back to Mark's talk from just the previous talk, I'm talking about delivery from, in this case, Kafka through Spark to a downstream data store. I'm not talking about the problems of upstream delivery into Kafka as not transactional. So you can get exactly once semantics in the sense of you won't lose data, you won't repeat data. In a sharded system, if you have a global view of it, it is still possible at any one time to observe that one shard is behind another. If you're sharding by customer, they're never going to see that. They're never going to see even that, right? They're going to see a consistent view of the world because their view of the world is tailored to one shard. But in any case, you're not going to lose data and you're not going to repeat data. So how does this work for the single database case? This slide is basically a compressed version of my previous talk at Spark Summit. So if this is a little fast, go look it up on YouTube for a refresher. If you're not familiar with Kafka, you can think of offset ranges here as being just an identifier for a batch of data that I can go back upstream and get exactly that same data over again, right? So I'm going to keep a table of these offset ranges in my database. When I'm going to do my for each partition to output Spark results, I'm going to do that in a database transaction. And I'm going to write my Spark results, and I'm going to update my record of offsets. And if those offsets weren't what I expected, in other words, I've somehow repeated the same batch of data again, I just roll back. And because they're in a transaction, they're in sync, I'm never going to lose data, I'm never going to repeat data. In a failure situation, I just go find whatever my high water mark was, the furthest along offset, and go back and get whatever data is remaining after that offset, recalculate everything, reinsert it. Clearly, this only works if your calculations are deterministic. Hopefully, they are. OK, so if I'm in a distributed situation, there are some minor additional things to pay attention to here. The first thing is I want my Spark partitioning to match my database partitioning. Second thing is, because I'm doing transactions on each worker, I'm going to keep a table of offsets on each worker. And that table is going to have the complete state of offsets that resulted in those results for each shard, right? In a failure situation, I have to do recovery. I'm going to go look at whatever the highest offset range was across all workers. What's going to end up happening is some shards are going to be behind others. I go back and grab a batch of data that spans that gap. I recalculate everything. I go and write results. And when I'm writing, I skip anything except the shard that was lagging behind, right? At which point, things are caught up, and I can start my streaming job with no loss of data and no repetition of results. So how do I go about actually implementing this? So Spark custom partitioners have two methods that are common to all of them. The first one is, how many pieces am I going to split my data into? Number of partitions, right? In this case, it's going to be the same between Spark and my database. Second method here is, I've got a piece of data, I get a key from it, I need to know which partition to send it to, right? This third method here is not built into Spark, but given that when I'm in that for each partition loop, I know my Spark partition, but I need to know which database worker and shard to go talk to. This custom partitioner already has that lookup information, so I might as well have a method to be able to do the lookup in both directions. OK, so because Citus is open source and because Postgres is open source, I can go read the code, figure out what hash function they're using. It's a pretty common hash function. Because Citus keeps its metadata in just regular old Postgres tables, I can do a query against those tables at the time I create an instance of this partitioner, build an efficient lookup array, and then use that array at runtime. So I got this query. You don't have to read it now. You can go back and look at it later if you need it. I've built this array to do my lookups in. I have a given key from my data. I hash it. Let's say I have a hash value of -2. I look down this array. I see, oh, -1. It's going to fall into that bucket. So it's shard 10/2009. Very straightforward. If I'm going the other way, I'm working on Spark partition ID 4. I just index into that array directly, look at the fourth entry there. I can see, oh, I need to talk to host 2, and the shard that I'm going to be writing to is 10/2011. If this sounds like kind of a pain in the butt to you, I've open sourced the code for this custom partitioner. It's available in the GitHub link at the end of the slides. OK, so what about the offsets table? What does that actually look like here? So this is an example of a situation where there's been some kind of failure. I have pulled all of the rows from the offsets table from all of the workers back to one place so that I can look at them, right? You can see that I've got an entry for every Spark application, for every Kafka topic, for every Kafka partition, for every shard. So I have a complete view of the state of upstream data that was used to arrive at the results that I'm currently at. And we can tell that this impressions 10/2010 is lagging behind because it's at offset 19 when it should be at 20, and then the other partition is at offset 18 when it should be at 20. So again, what am I going to do here? I'm going to go back to Kafka. I'm going to grab the offset ranges for partition 0 between 19 and 20, and for partition 1 between 18 and 20. I'm going to go recalculate everything. The reason I'm going to recalculate everything from all available data is because there may have been shuffles involved, right? And writes to anything other than the shard that is lagging are just going to get skipped because their offset isn't going to be what's expected. So this is a reasonable amount of engineering work. It's pretty straightforward. In all honesty, it's not a lot of code. Was it worth it? So it was definitely worth it because we got off of one RDS database, right? We went from one RDS node to 2 Citus nodes, doubled our write throughput, which is pretty okay. If you're sitting in the audience saying like 2 nodes, who cares? 2 nodes is what I need to solve this particular problem, right? I've seen reasonable benchmarks for 32 node systems. If I get to the point where I'm using 32 nodes to tell my customers how much money they're making, I've probably retired to the Bahamas by then. So on the read side, most of our queries are averaging in the 1 millisecond or under execution time, which is pretty all right. Always in the situations like this, there are going to be things that you wish you had known to begin with. So in our case, there are a couple of those. The first one here is entirely my fault. If you're moving from an existing database to a sharded database, it's super tempting to say, why don't I just add that column I want? And why don't I just drop that index I don't need? And why don't I add this other index that I do need? Don't do that, because if you do, it's hard to tell what's changed because you're sharding and what's changed because Cody's monkeying around with stuff. Second thing on this list, if you use Postgres, you're probably familiar with external connection poolers like PG Bouncer, because Postgres is a fork per connection model, not ePoll. You need to use PG Bouncer in front of workers as well, even if clients aren't connecting directly to them. The reason for that is, again, if you have one master query coming in that's hitting all shards, it's going to get multiplied. So you got 1 to 32, and then you got 10 master queries. Now you got 320 worker queries. Not a big deal, just something to be aware of. You need a connection pooler there. There is a little bit of cognitive overhead about what SQL features will work transparently in this situation. One example there being limit. If you're doing a limit and you don't have a sort, it doesn't make a lot of sense to push that limit down to the workers because you're not going to get reliable results. However, this kind of thing, because these underlying nodes are just Postgres databases, it's a lot easier to understand than a non-relational data store that gives you something that looks like SQL that has completely different performance characteristics, right? And the last thing on this list is just a minor nice to have. So given that you have hash distribution in order to get to a particular shard, it's often convenient to have that shard be a table that's partitioned according to date ranges so that you can do things like effectively drop the end of your retention, that sort of thing. You can do this manually with Postgres and table inheritance, but Citus doesn't automatically set that kind of thing up for you, and it is on the roadmap. And again, we are, in general, very satisfied with the solution. It bailed us out of being stuck on like literally hard limits on RDS. These things are just minor lessons learned. Looks like we have time for questions. There's a GitHub link if you want to try the code out.
So in your example, you were having Spark write to Postgres. And my understanding is that the standard JDBSec connector uses individual inserts. How do you find a way around that, like using the Postgres copy statement?
So you can use Postgres copy there. If you're doing destructive updates, that makes it somewhat less convenient. You can still do things like copy to a temporary table and then do your updates from there. We actually get reasonable enough write throughput just using JDBC directly to individual workers. We haven't had to jump through the hoops yet. Come on, I expected more trolling.
Sorry. I have a short question. So Citus seems to be using GPL3 license.
AGPL, even better.
Okay. So in that case, is there any alternative to Citus, like pure open source?
So look, like, I'm an attorney. I went to law school. I understand why AGPL sucks. It sucks. If you're a commercial business, it is understandable why you would choose AGPL. I'm not touching Citus code. There is no argument that they could possibly make that anything that I've said or done or shown to you today could in any way fall in the AGPL. I'm not your attorney and I'm not giving you legal advice, but like that's the reality of the situation there. They're not going to do that because I'm not modifying their code and then putting it on a publicly available server.
Does Citus support replication across data centers?
So the answer to does Citus support X is does Postgres support X? So if you are comfortable doing Postgres replication cross data center, then yes.
Just out of curiosity, as you know, there are a lot of mechanisms that are very similar with slightly different implementations. So for example, if you partition inside of Postgres and enable the parallelism from 9.6, right, it's conceptually very, very similar. Did you compare those two?
So we were looking at not only like read throughput, but like actual storage, right? And that, what you're talking about doesn't actually help the problem of like Amazon won't let me have more than 6 terabytes, right?
Okay.
Yeah.
Okay, we have time for a couple more questions if anyone wants to come up. Otherwise, let's give a round of applause to Cody.
All right, cool, thanks for your time.